Cool. So just putting up this disclaimer again that all of the opinions are my own and not that of my employer. And so in the last session, I talked to you about variational autoencoders and hierarchical variational autoencoders, and we talked about inference and inference networks. And we saw that credit assignment, when you want to assign credit to the latents, is a very hard problem, and that kind of training inference networks, or the encoder of my VAE, and the generative model, which is the decoder jointly, is like trying to hit a moving target because kind of one tries to fit the other, and then they kind of have to explain each other, and that can be quite difficult. But somehow we do need this inference network to make training efficient, or do we? And one idea that I mentioned then was this idea of just fixing the inference network, and then the training becomes suddenly much simpler because we only have to train the generative model, and the generative model then just has to explain something, and it's kind of, I mean, it's not really a supervised learning problem, but it kind of becomes more like it in a sense, because it just has to learn to undo the inference that we did. And then I said that somehow ties in with diffusion models, and I'll explain to you in the course of this lecture what I mean by this. And I should also thank Andrew Mni from DeepMind to kind of introduce this perspective to me, and kind of also this whole angle on inference as credit assignment that I've been talking about was hugely inspired by him. As yesterday, if you have any questions, please jump in. I much rather we skip a couple of slides in the end, and you explain everything. You understand everything that we discussed up to that point. But hopefully it shouldn't be too much, and we should be able to make it through comfortably. So what's the motivation? I said we just fix the inference network, and then training becomes much simpler, but of course that's kind of a lie, because you have to think about what are the features that you should use for inference, because somehow you still need to have something that happens there that makes sense. And handcrafting, as we've learned in machine learning over and over again, seems to be like a terrible idea, because whenever you handcraft something, ultimately it will be superseded by something better that's just learned. So we don't want to handcraft these features for each layer, and then one very easy idea could be, well, we could just copy the information from the previous layer and then remove a little bit of that information. And then if we keep on doing that, in the end, we end up with Gaussian noise, which was kind of the prior in a VAE. But on the way, we have information at different stages in each layer, and that somehow then allows us to generate, hopefully. And doing something like that, copying is easy, and adding noise or corrupting something and removing a little bit of information is easy. It also, in VAEs, we saw it's difficult to do credit assignment if you have different layers, because like the different layers compete for who should explain what, and then you have to come up with these schedules and explaining like how much information should be in each layer. If you fix everything and you just say that this much noise is added per layer, that means each layer has a clearly defined role, because it has exactly this much amount of noise, which means it removes exactly this much of information on average from the data. And then the generative model in the reverse direction somehow learns to undo this corruption. It only has to undo a little bit of corruption each time, so it has to solve a simple problem at each step in a way. And that is kind of what diffusion models do. So in the diffusion model, we start out with clean data on the left, and then we have pure noise on the right. And in between, we have this kind of fixed forward diffusion that is in turquoise, where at each step, you add a little bit of noise to the image that you had in the previous step. So you have your clean image on the left, then you add a little bit of noise, you have a slightly noisy cat, you add a little bit of more noise, you have a slightly more noisy cat, and then at the end, the cat completely disappears. And then the denoising direction, which is this kind of violet lilac color, learns to undo this process, and it basically takes the pure noise, makes it slightly less noisy, and so on, until you end up with the clean cat again. And you also see the most important piece of advice that I can give you if you want to work in diffusion models is that you should either have a cat or have access to a cat, because for each paper you'll need these kind of pictures. And everyone seems to use their own cat, so you see the different cats of the different researchers. There seems to be a vital part of research in this area. I don't have a cat, so I had luckily access to this cat to take this picture. And yeah. Right, and so how does this tie in with VAEs? And I should put like very, very large quotation marks around this call-out box. In VAEs, you have the clean image in the bottom, and you have the pure noise in the top, and somehow you can think of, well, diffusion is somehow this direction that goes up, and denoising is somehow the direction that goes down. And that's somehow how we'll tie tie kind of the thoughts about VAEs and the thoughts about diffusion models together. But there's really big quotation marks around this. Okay, so a second disclaimer, which is that this is only a brief introduction to diffusion models, and it kind of comes from this inference perspective. And there's this really, really great tutorial that Kreis, Gao, and Wadat gave at CVPR 2022, and I think it's 3 or 4 hours long, and covers much, much more than I'll cover in this lecture. So I'm taking ideas that they present, and I think they have some very good illustrations, so I'll use ideas from that. But I'll focus purely on what is called the discrete time formulation of diffusion models. I will not talk about scores, and I will also not touch upon like this whole ODE, SDE, so ordinary differential equation, stochastic differential equation business that is going on in this field as well. If you want to learn about those, then I think this tutorial is really, really amazing, and then some of the other references here are kind of some of the seminal papers that introduce these models. So how does a diffusion process work? So we first define a fixed forward noising process, and that will be illustrated, so here we have the cat again. We'll introduce the notation that we have time and different time steps. And so we're in this discrete time step formulation where basically we start out at time 0. And then time 1 is when we added the first bit of noise. Time 2 is when we added the second bit of noise, and so on. And our process runs for a finite number of steps, capital T. And capital T is then assumed to be pure noise. And then we have, as I said, at each step, we add a bit of noise. And the simplest noise you can add is Gaussian noise. And so that's exactly what this equation tells us. So going from one time step to the next time step, so going from t minus 1 to t, we downscale the mean a little bit, and we add a little bit of noise. And so here in the top, you can see that we denote this by q, and this is kind of similar to the q that we had in the inference direction, but now this is fixed. So here we choose a fixed schedule of these betas, because the beta are basically the only parameters that determine what's going on here. We fix that at the beginning, and then that's basically a hyperparameter of our model in the same way that other schedules are hyperparameters of models. Like if you have a learning rate schedule or something like that. And over the course, we'll see what kind of choices make sense for beta, but typically you start out with a very small beta in the beginning, and then it slowly increases over time, so as you do more and more of these steps. And as you can see, if beta is 0, then the mean is just the previous image, and the variance that we add is 0, so we don't add any noise. So if it's very small, then we only downscale the mean a little bit, we only add a little bit of noise. And then, as I said, over kind of as we progress from left to right, we kind of keep adding more and more noise, and this beta slowly goes up. And there's different schedules that people have explored, and that's something that basically several papers have been written about how to do this. Yes, question? Yeah, so the question was, here we only have one parameter that basically determines both the mean and the variance. That's not strictly necessary. Those could be different parameters, but people have found that tying them together works well, and the fewer parameters you have that you need to tweak, the better. So I think this is just a convenience choice, but in principle, you could choose them independently. And then when you have this kind of single conditional distribution, you can tie them together, and you can come up with this joint distribution by using the rule of probability, where you just have this whole q of x1 to xt can be written as a sequence of conditionals by just breaking them apart. And because everything is kind of Markovian and just depends on the previous image, you just get this very simple structure where the next image just depends on the previous image. Okay, but iterative sampling, so this is still for kind of the generation process where we start from the clean image and we go to the noisy image, so where we destroy information. And if I want to, for example, I want to go from my clean cat to something that's very noisy, and let's say I have 1,000 steps, then it seems very inefficient and very slow to kind of first sample one time step, and the next one, until I'm at the point where I want to go. Ideally, we would be able to jump directly from the clean image to the very noised image. And because everything is Gaussian, you might already guess that there's a trick that basically we can compute this efficiently, and that's exactly also the reason why we choose the noise to be Gaussian and independent per pixel, because then we can actually do this jump in one step, and we don't have to iteratively sample each of those. And so let's just look at how this is done. So let's just go from basically the first image, which is the clean cat, to the twice noised version. So that's just q of x2 given x0. And then that's a marginal over the joint of x1 and x2 given x0, where we integrate out x1. And then you can decompose it because everything factorizes in this way that I described earlier. And we know that both of these noising distributions are Gaussians. So this is just a product of two Gaussians, and then we marginalize over that. So there's two ways you can compute this if you want to do it by hand. I guess one is you can use a convolution theorem and say, well, this is a convolution of two Gaussians, if you squint at it. And we know that a convolution of two Gaussians, where the mean is linear, is another Gaussian. Or you could think of it as, well, this is a product of two Gaussians, which is a Gaussian. And then we marginalize out over a Gaussian, which is also, again, another Gaussian. So what we get in the end is a Gaussian where the mean and the standard deviation are given by these expressions. And if you go through the mathematics, you see that, okay, for the mean, basically we just multiply the means, and then for the standard deviation, it's slightly more complicated. And if you go through the mathematics yourself, you can do that as an exercise if you want, then that's kind of the result that you get. But it's nice that it's a clean, closed form solution where we can jump directly from x0 to x2. And then obviously we can't just jump from x0 to x2, we can jump to any t that we want, and we just have to repeat this process, but luckily there's a pattern to it, and so jumping from x0 to xt, we introduce this alpha, and this alpha will be this product of 1 minus beta. So here we had 1 minus beta 1, 1 minus beta 2, and then the square root of that. And then you think, okay, if I do that again, then I add the 1 minus beta 3, and then I add 1 minus beta 4, and the same happens in the variance as well, which is how you end up with this formula. So this alpha is a very complicated thing because it's a product of all of these things, but the betas are fixed because that's exactly the schedule that you choose. And so you basically can pre-compute this, and then you have that just lying around. So that's, if you look at the code base of a diffusion model, that's exactly what they would do. They would say compute beta schedule, and then they get all of these alphas, and then they have all of these values fixed, and it's just an array, and then you just pick, if I want to jump to entry 633, then I'm just gonna look up that value, and that's the alpha that I'm gonna use to add the noise here. And we choose the beta schedule in such a way that if we compute this product, and then go towards the last time step, so if I have a very, very, very big product, that this alpha bar t, capital T, goes to 0. And if that goes to 0, then if you plug it into equation, then you see that the mean goes to 0, and the standard deviation goes to 1, which is exactly what we want, which is that at the end of the diffusion process, we want to end up with pure noise that's just identically drawn for each pixel. Okay, and then again the question, how do we actually sample from this in practice? And that's exactly the formula that we discussed yesterday, where you have the mean and the scale, and you draw a sample from a standard normal, and then you shift the mean and you multiply the scale. And so in terms of formula, it's the formula here, and that's just taken from above basically. And in terms of pictures, you have the clean cat, you have the noise on the right-hand side, and then you get the kind of slightly noisy cat, and depending on how the alphas are weighted, you get a slightly more noisy cat or a slightly less noisy cat. And one thing to notice here is that you have this expression that connects the original image, the noised image at some intermediate point in time, and pure noise. So all of these three quantities are somehow connected with each other through this equation. And given two of these, if I have x0 and epsilon, I can compute xt as we just did. But if for some reason I had xt and epsilon, then I could compute what is x0. Or if I had x0 and xt, then I could compute what was the noise that I added. So they're all nicely linked to each other, and this will become important, so that's why I'm stressing it so much. Maybe let's get some intuition for what this noising process does and why it makes kind of intuitively sense to use this for images. So this is the formula for the noising process. And this is a visualization that I took from this tutorial because I really liked it. You can go into the Fourier space of this. So you can take the x's, which are just images, and you can look at their spatial Fourier transform. And the Fourier transform was already introduced by Xavi, so I'm always relying on him to have explained something to you, which is really nice. And if you look at this Fourier transform of an image, so this is just a 1D image, so a bit boring. It typically looks something like this. There will be a peak in the middle, which means that low frequencies have a lot of energy, and that high frequencies have kind of less energy, because typically if you look at an image, there's clear structure, there's like here there's these columns in the room and so on, and then there's like some fine-grained detail, but that's typically much less important in a sense. And the kind of identical Gaussian noise that we draw has a constant energy for all frequencies. That's just something that I tell you that is the case. You can compute that as well. And then we can ask, okay, if we're now in the regime where I'm quite early, so I'm still very close to the very clean cat. In that case, the alpha bar t is going to be close to 1. And if I'm close to 1, then I'm almost at the original image and I almost don't add any noise. And if you look at it in terms of the Fourier spectrum of these two things, you have the blue curve, which is basically unchanged, and a very, very downscaled version of the red curve from the noise. And if you add the two together, you see that most of the low frequency spectrum is still visible, so all of the coarse detail in the image is clear. But then the high frequency details are somehow drowned out by the noise. So that's exactly what's going on here. So the high frequency information here is kind of drowned out, and so that's also kind of, if you look at the image and there's a little bit of noise, then you can't tell exactly what was the pixel value here because you added a little bit of noise, but you still see it's a cat. And then if you go to very large values of t, then alpha bar t is almost 0, which means that we are not using much of the original image, we're only looking at the noise basically. And in terms of the Fourier spectrum, that means adding things, for example, like this, and then you see that only the very center of this frequency spectrum, so only the very, very low frequencies are still kind of less perturbed, whereas everything else is drowned out. And that means that we might just make out it's the outline of a cat, but we don't even see if its eyes are closed or open and so on. And that's kind of the intuition of why adding IID Gaussian noise in this way kind of makes sense, because we kind of drown out. It's similar to in a VAE where I explained to you, we have in the lower levels, we look at the fine-grained details, and at the upper layers, we look at coarse-grained details, and that's the same here. When we're almost pure noise, we only have coarse details, and when we have only little noise, then we also see all of the fine details. Okay, so now we can ask the question, so I gave you this, we have an initial data distribution, we have this transition probability that goes from one step to the other, or we can make larger jumps. How does the marginal distribution at a certain point in time look like? Well, we can compute that. That's basically just an integral over this joint. And then we can use that we can make this jump and integrate it over the data distribution. And in principle, this will be intractable because the data distribution, which is on the very left, so this is just for a single pixel, can look very complicated. And then you see as you kind of add more noise, it kind of goes more and more to the standard normal distribution. And you can think of the expression on the left here somewhat as a convolution kernel where you convolve with the Gaussian of increasing strength. And so at the one end, you have a lot of noise and you only get the Gaussian. On the other hand, you only like mildly tune out these details. And how do you sample from this? Well, that we already described. You sample the original image from the data, or the original pixel value from the data from this Q of x0. So my one pixel of the cat. And then I can jump using this transition probability and sample a value xt for that, and then I can throw the original x0 away, and then I have my xt. Or if I integrate over it, that's the proper marginalization way of doing it. And you see that all of these marginal distributions in between are also intractable in a sense. Like at the very right, we know it's a Gaussian because that's how we constructed it, but everything in between we don't know what the distribution is going to look like. We only know the transition probability, which is a Gaussian. But we don't know what Q of x1 is, what Q of x2 is, and so on, because it convolves the original data distribution, and the original data distribution was complicated. Okay, so that was the noising process. Now we can try to go the other direction. We want to denoise. So starting from, that's the more interesting one because that's what we actually care about. So far, that was just taking an image, which is somehow we want to get out images of our model, and we noise it. So now we do the opposite. We start with noise, and we kind of want to go to an image, and that's where the learning comes in and where we have our model. And for that, we need kind of inverse probabilities of transitioning. So starting from a sample on the right, which we can sample because by construction it's just a Gaussian. We take a sample from that Gaussian, and then we can plug it into the inverse direction. So we have this inverse probability distribution down here that is a conditional, and then basically we can iteratively sample and go the other way. And something like this is typically referred to as ancestral sampling because we start kind of with the ancestor and then we kind of go forward through time. And here we kind of iteratively sample from this. And then I think the red crosses here are basically the samples that I've chosen at each step because I'm showing you the full distribution, but actually you only get these individual samples, which are the red crosses. And obviously this Q of t-1 of x t-1 given xt, that's the true and intractable denoising distribution. Which means we'll have to approximate this object. And it's important to note that in true machine learning fashion, we have overloaded the letter Q, because so far Q was always the noising process. And it was Q going from xt to, no, Q from xt given xt minus 1. So that was basically taking a less noisy version and adding more noise. And now this Q refers to the opposite, which is taking xt and moving it to xt minus 1, so denoising it. So you always have to look at like which way are the arguments around to make sure which one is which, but that's the notation that's used in the literature, so I try to stick with it, that if you read the paper, you understand this. So what is this? This true denoising distribution? So this is kind of a multimodal distribution that can be quite complicated. And it's kind of the inverse of this very simple noising process. So if we are in this picture, then basically it would be going from one slightly noisy cat to a slightly less noisy cat. How can we see that it's intractable? Well, we can use Bayes' rule to basically connect the two. So on the left, we have this true denoising distribution, which is complicated. And then we can express it using Bayes' rule, or alternatively, you can say using the product rule of probability to say, well, this is something like a prior times a likelihood kind of thing. So that would be the Bayes' rule view of it, I guess. And there you have two terms. You have this Gaussian noising that we introduced in the beginning. And then we have this intractable marginal distribution, where I already showed you that that's a quite complicated thing that we can't evaluate. And so obviously, if you take the product of these two, it's going to be something complicated. So that's why it's intractable and why we can't use it. But luckily, there is something which is typically referred to as the tractable denoising distribution. And that's almost the same, but we added a conditioning on x0 here. And it turns out that if you go through the maths, and I'm not going to show this to you, this becomes a Gaussian. And Gaussians is something that's nice that we can work with. And now the question is, why does it make sense that if we add x0 in the conditioning set here, why does that make the problem tractable and give us this tractable distribution? Well, so we think back about this equation that I showed you earlier, where I said it connects all of the three properties that we have. And so if we go to our image of the cats, the thing that we want is basically we want to go from xt to xt minus 1. And we don't know this arrow here. That's the Q that is the complicated intractable denoising distribution. If we also add the conditioning on x0, then that becomes the thing that I tell you is tractable. And we can use the kind of equation to sample that we had initially to see why this makes sense. So this is the equation that connects all of the three quantities. So given if we have the clean image and the noise, then we can compute the xt. And we can do the same for the image before. If we had the true noise and we have the clean image, then we can compute xt minus 1. But what we actually have is, according to kind of the conditioning information that we're providing, which is xt and x0. So we have xt and x0 in this equation, but we don't have epsilon, which is the noise, because that's kind of the thing that we added that's difficult to remove. That's the thing that we want to remove. And in the same way for the other equation, we have the x0, but actually the xt minus 1 is the thing we want to compute, and we also don't have the noise. But as you can see in the top equation here, there's only one unknown. So we can compute the epsilon because we have the xt and we know what the clean image is. And if you know what the noised image is and you know what the clean image is, you can compute what the noise is. And then you can take the noise and plug it into the other equation, and then you have the clean image, and now you also know the noise, so you can compute what xt minus 1 is. And then suddenly you know what xt minus 1 is. Whereas if we didn't know what x0 was, then in the top equation, it would have been hopeless because we would have two unknowns, basically. And that's kind of the intuition why the one distribution is complicated, but then if we add conditioning on x0, which is the clean image, why suddenly things become much simpler. And it kind of intuitively also makes sense that if you know the clean image and you know the dirty image, that the problem is easier. What's the reason why we can't just use this tractable distribution instead of the intractable one? Thinking about kind of what the problem is that we actually try to solve.
We don't know the image.
Exactly. So we don't. The whole point is that we start with noise and we want the clean image. So we naturally don't have access to x0. So if we had access to x0, then the solution was already there, so we wouldn't actually have to go through all of this. But we could go through the exercise of doing it, as I just showed you. But the whole point is that we don't have that. So somehow we can't use that. But the Q of xt minus 1 given xt is intractable. And so what you then do is, well, as always in machine learning, if something's intractable, you come up with a tractable distribution. And the way that you do is that you introduce this distribution, which is now called p theta of xt minus 1 given xt, and that's kind of our generative model that we'll be learning. And in terms of VAEs, you can think of it as the decoder that goes from the latent to the image, and so here we go from the noisier version of the image to the slightly less noisy version of the image. And it turns out, and you can also make this mathematically more rigorous, that if you make time steps small enough, so if the noise that you add is really tiny, then using a Gaussian is a good approximation for this transition probability. It's a bad transition if you go from if you make huge steps, but if you make tiny steps, then being Gaussian at each of these steps is a reasonable enough estimate. And note that the Gaussian that we're using will have a fixed scalar noise scale. So this is just a single value of sigma, which is time dependent, but it's the same for all the images. And that the mean will be given by a neural network, and this will be a so-called UNet, and I'll show you later how that typically looks like. And then you can compute a joint distribution. So if it's conditional, we know it's Markovian because one given the other, we can kind of follow this chain, so you can kind of write down the joint distribution like this. So how should we parameterize this distribution? So I said we parameterize it by having a neural network for the mean. If you look at this, it looks very similar to this tractable denoising distribution, which also had a mean and some variance, but it depended on this x0, which we don't have. So here it depends on the x0, where this does not. And it turns out that what you can do, similar to what Xavier was saying, there's this term that we can't compute, so we just throw it away. This is a thing that we know how to compute. So maybe during training we have x0. So maybe let's just try to approximate that and then hope that later on we can work with that. So the problem is we don't have access to x0, and the solution is that we're going to use a neural network to predict it. And the formula for the mean, then basically comparing these two and matching terms looks something like this. And you're again using these relations between these three, or if you have xt minus 1, these six values, where you have the noised image xt, because that's the thing that we start out with. We want to do one step to xt minus 1. We don't have the original image x0. We don't have the noise. But what we do is we train a neural network to predict what the noise would have been, which gives us access to epsilon, and then we get the x0, and then the x0 we can plug into the other equation where we have x0 and the predicted noise, and then that gives us xt minus 1. And that's quite a roundabout way to then parameterizing this mean, but if you plug all of this together and you go through the algebra, then that's the formula for the mean that kind of makes sense. So you predict the noise, you take your noisy image, you predict what the noise could have been, and they use that together with these these two equations with the 6 variables that are all connected to derive what is the mean of xt minus 1 if I have xt and I know the noise. And that's exactly the equation that comes out. So it's not important to kind of follow exactly this, but it's the structure that's important in the sense of like what depends on what. And I told you we'll use this UNet architecture. So what happens here is that you have the noisy cat, and the noisy cat goes into this architecture which basically has a bottleneck where you have a convolutional network that starts out with a quite high width or high resolution, and then goes down to lower resolution, and then goes back up to higher resolution, and then spits out something which has the same dimensions as the image. But instead of predicting an image, you predict the noise. And this is a very similar architecture to what has been used, for example, in the semantic segmentation, where you put in the video of the car that's driving around, and then you segment it into this is a street, this is people, and so on. It has the same dimensions as the original input, but it's a segmentation mask. And in this case, it's just the noise that likely has been used to basically create this image. And it sounds very counterintuitive that you can do that, but it turns out practically that actually works. The important thing is that like if you have a very clean cat, which only has a little bit of noise, then obviously the prediction problem is different than if you start with almost pure noise and you can barely make out the cat, because then the noise that you predict is much larger. And so the network needs to know at what stage in the process are we, and because we fixed the noising process, we kind of know what the scale of the noise at each time step will be, so that's kind of what we know. And so we tell the network about it by inputting it the time step, or equally you could tell it that's the noise scale that we're looking for, because that's what we know because we fixed the noising process for this whole process. And then in addition, you can also add in other conditioning information. That can be the class label if you only want to produce cats. It can be text if you are in like the stable diffusion setting and you want to have text conditional generation. That basically goes together with the time, and then it goes into these different layers of the network. And typically how this is implemented is that there will be some form of normalization layer in these networks, and because batch norm isn't really working that well, people have switched to other forms of normalization like layer norm or group normalization. And there's a form of adaptive group normalization where basically you can take additional information and then scale the normalization layer accordingly using the information from the time and the conditioning, and that's kind of all jointly trained. Okay, so if we have all of this and assume that this model has been trained, how does the whole picture then fit together? So on the left we have the clean image, on the right we have the noise. In the top you see the noising, which is the fixed distribution that we basically chose for these transitions. And in the bottom is basically now the model that we've trained, where you always denoise a tiny bit. And so how does this look like in the bottom? So now I'm going the other way around from left to right, unfortunately. So we take the noise image, we feed it into the network, it predicts the noise, and then we have a skip connection where, given the noise and kind of these things and the XT, we put it together, and we get a slightly less noised version. And then we take that and we feed it into this network again. It again predicts some noise, and then the noise and the kind of noised version of the image, together with those, we can predict the slightly less noised version and so on. And then we do this 100 times, or I think in the original papers they do it 1,000 times to go from pure noise to the image. So you have to evaluate this quite large neural network 1,000 times, and that's why sampling in these models can be very slow, and there's a lot of research going on into kind of making it faster so that instead of doing it 1,000 times and removing a tiny bit of noise each time, you actually do it only tens of times. So the way that I plotted it here with only 7 cats, that's very unrealistic. Typically this plot would be very, 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 very wide, and you have to put in a lot of compute. And in terms of formula, or if you look at the algorithm box from the paper, it just looks like this. You start from the top with pure noise, and then you go through these sampling steps where basically you the third line is a detail that we can kind of ignore. And in the fourth line, basically we feed the image into our network that predicts the epsilon, and then we put these things together to get this mean that we want to predict, and then basically we can sample from that, or we can just take the mean, and that's the prediction for xt minus 1. And then we just repeat this, just like in the picture above. Okay, so that's if the model is already trained. Now the question is, how do we train this model? I told you how the process works, how if everything is trained, you can sample from the model. How do you actually train this? So what we've done is we fixed the noising schedule, and now we need to learn the learner parameters theta of this inverse denoising process. And it turns out that we again can use maximum marginal likelihood to do that. And again, this will be intractable, and then we have to derive a lower bound, and this will be an elbow, an evidence lower bound in the same way or in a similar way that we did before, where you introduce a variational distribution, and it will turn out that the variational distribution that we'll introduce is exactly the variational distribution that we had earlier, which was this tractable inverse noise, or this tractable denoising distribution. That would be the variational distribution that we use. And then basically it's all related by Jensen's inequality, in that you say the right-hand side is a lower bound to the upper side, and then we try to maximize the right-hand side, and that will kind of maximize the left-hand side as well. And that gives us a training objective. And the mathematics is slightly more complicated than I showed you for the VAE, but it follows roughly the same principles. And you have to make the right choices at the right times, but then you can decompose it and you end up with an objective. And then people found out that that objective, which maximizes the marginal likelihood, gives you good likelihoods, but it doesn't give you images that look very nice. And so in practice, they use a much simpler objective, which looks like this, which structurally is very similar to the objective that comes out from the top, but some terms are missing. And this is kind of the objective that everyone uses in practice. So let's look what this objective actually means. It's a very simple training objective. There's an expectation where we sample a lot of things, and then it's just a mean squared error. It's just an L2 term. And the L2 term is between the noise that we use to noise an image and the prediction of the network, what the noise was when I give it the noised image. So how does this process work? So it's basically just an L2 or noise prediction, which is funny to think about. We learn to predict noise to predict a clean image. But it turns out that that's the most efficient and the best way of doing it. You could do it differently, but it turns out that this actually works best in practice. So in this expectation, we first draw an image from the data set. And it's by chance, again, this cat. And then you draw some noise, which you can also do, which is very simple. And then you think, what time step do I want to take that I want to noise to, that I want to learn the model on? And I'm just going to use some uniform distribution on that. So I'm going to use, let's say, time step 633. And then I can compute this alpha, because that's the noising schedule that we fixed. So I know what this value is. And then with all of these three values together, I can again use my favorite equation, where I connect all of these quantities. I can take my clean cat, the noise, the alphas, and then compute what the slightly noised version of the cat is. That's xt. And you see that xt is also the argument that we feed into this noise prediction network. So we have the noised cat, we feed it into the network, and we get a prediction for the noise. That's the thing that comes out here on the right. But we also, in this expectation, we also drew the noise. So we know what the noise is that we use to noise the cat. So we know what the ground truth noise is. And now we have a prediction for the noise. And then you can take the two together, subtract them, and then say, okay, I want to minimize the difference between the two. And that's exactly what this objective does. And then when this objective is perfectly optimized, then the network perfectly can know what was the noise that would have been used in the noised image. And then later on, we don't, like in this prediction of the network, we don't need the clean image, because we just need xt. And xt can also come from the other direction, where we start with pure noise. And then the network does exactly the same thing of predicting, well, what could the noise have been that this image has been noised by? Although there wasn't an image, there was just pure noise. And then you can use this to kind of denoise the image iteratively, as we discussed before. And this is how it looks like in an algorithm. It's exactly what I described. You sample the clean image, you sample a time step, you sample the noise, you compute the noised image, you plug it into this equation, and then you take a gradient of that L2 term, and then you just optimize that using your favorite optimizer. Okay. Are there any questions up to this point? Yes?
So earlier you argued that the model is trying to predict the t minus 1 step from t step.
Yep.
And here it seems like from t you're trying to predict the original image.
You mean here, or where do you? Yeah, so I guess the thing is that this noise is always the same noise scale, and it's basically only this alpha t that tells you if I'm connecting it to the original image or where I'm jumping to, basically. And that's how you can tie them together. So you're not trying to predict the clean image, you're trying, so you can use the same noise, and by scaling it appropriately, you can either use it to jump back to the original image, or you can use it to jump to the xt minus 1. It predicts the noise, and then exactly you could make it to use larger jumps, but it becomes less and less accurate as you do that, because the noise prediction will not be perfect. And so if it was perfect noise prediction, you could use a single step. But if it's not perfect, then you have to do smaller steps so that you can correct basically at each step. And that's the reason why you do it like that. And it ties in with this, it's a good approximation for to use a Gaussian for this intractable denoising distribution. If you have small time steps, but you have large time steps, then the distribution becomes very complicated, and then your jump will be very bad. And that's the main reason. But the noise is basically kind of scaleless, or it lives on the scale that's from the standard normal, and it's only the prefactor that determines whether you connect what you connect it to, if that makes sense. Okay. Any other questions? Yes.
just this philosophy, but in a contrastive learning framework. So if I had fixed noising parameters and additional contrastive learning techniques, I could even enhance this technique even further. Maybe you could have it in one architecture, but yeah, could you do that in a contrastive learning framework?
So what would be the things that you contrast?
So like you could put in the image of the cat 10 times noise at a fix, just like you do with the diffusion process.
Yeah.
You get the same results basically if you do it that way.
Yeah.
Or is it just completely different?
It's a good question. I haven't thought about it like this. I think I need to think a bit longer to give you a proper answer, but we can discuss it later. Any other questions? Okay. So as I said, there's a long derivation that basically derives this objective, and I won't go through it. They are in here and they're also in the papers. But just to give you a very brief taste of how it looks like, it becomes very messy with lots of terms. But all of these terms are quite simple. So I just want to focus on the top bit, and then I'm not going to show you the other remaining, I think, 5 slides that do this derivation. So this was the maximum likelihood objective on the top, and we did a posterior approximation using this Q that depends on x0, and then we can factorize it. And so that's a lower bound. And then if you group the terms, you find that they will find 3 terms. One is a term that's basically the almost clean cat to the clean cat. That's something like a reconstruction term in a VAE. Then there's something that acts on the very left, that's LT, that basically connects to the prior distribution, which is this Gaussian. So this is kind of a prior matching term. And then you have these many, many denoising matching terms in the middle. And the denoising matching terms are what I meant earlier when I said we can make it more rigorous, that we fit our model, which is p theta of xt minus 1 given xt. So that's the denoising model. We fit that to the tractable denoising distribution, which is the thing here on the left. So if you minimize, or if you choose the minus signs rightly and you optimize this in the right way, this KL will go to 0, which means that you are perfectly matching this distribution. This is just the intuition, and then there's lots of maths to make this exact and go through the algebra, which we will not look at. Yeah, and in the very end, you end up with an objective that looks like at the top. So you see it as the same structure. We sample x0 and epsilon in the same way. You have this L2 distance between the noise that we put in and the noise prediction. And then you have a prefactor that's not 1, that came out of the derivation. And then you have some constant terms that don't depend on the parameters of theta. And then the simplified version of that is saying, okay, we're just going to keep the L2. We're going to weight everything in the same way. We don't use this non-1 prefactor. And also additionally, you have a lot of these terms, because this is just one of the many terms in this sum. We're going to subsample, and at each step we're only going to optimize one of these terms, because we only pick a single time step here. So we only learn to denoise from step 633 in one step, and then the next time maybe we noise the cat only a little bit, and then we try to predict the noise, and then we go to pure noise and we try to predict. And so at each step of training, you don't go through this whole noising process and denoising process. You only jump to a single point and optimize for that. And then you jump to a different point in the next step and you optimize that, and so on. Okay, so that was the simplified objective. And then we have the training and the sampling, which were both very straightforward. The training is very quick because we only do it for one time step, whereas in the sampling, we actually need to iteratively go through this process. And that can take tens or hundreds or thousands of steps. And this I already explained. So what can you do with these models? That's going back to kind of the slide that I showed you in the very beginning. Yes, question?
Sorry, about the previous slide.
Yeah.
So you said that you select randomly this key point,
Mm-hmm.
but maybe it is better to select it more formal way, so we can learn less noisy images first and then more and more noisy, because it seems like it is.
Yeah. So the question was about so there's a lot of choices that I made, and I presented them, and I didn't talk about other choices that you can make. So one choice was that I'm going to uniformly sample t here, which means I might in the beginning, I uniformly sample the different time steps, and maybe it's better to have a curriculum where you start with only slightly noised images, so the network has it a bit simpler in the beginning because it knows what a clean image is, and it's very simple to get the noise from that. And then we can make it more and more difficult and jump to later and data times over time. And that's a choice you can make, and you can try out, and then you find that it doesn't really make a huge difference. In some cases, for example, it could be that sampling earlier times more often than later times might be important. And in some cases it's better, and in some cases it's worse. So this is another schedule that you need to optimize and do a hyperparameter sweep over, basically. This is just a decent starting point that you can use. There's also, again, we are estimating quantities here, so there's a bias and variance thing going on as well. We're biased because we threw away this prefactor, but then also there might be larger variance if we draw certain time steps too often. And then you can choose your schedule for the T's to minimize variance, and that's another paper, or two other papers. So each of these choices, again, there's lots of literature around this on how you choose this, and this is just the simplest thing that Jonathan Ho and colleagues came up in 2020 that was a good starting point. And since then, I mean, that's 2020. You know how much work has been done on diffusion, and it's really exploding, and every day there's 10 new papers on arXiv, and they all look at these different choices, basically. And so going back to the slide that I showed basically yesterday morning, one of the cool things that these models allow us is to do image generation to a very high quality and in a text conditional way that we didn't have before, which is very exciting. And we see diffusion models, I guess, used more and more, and this was just a kind of brief introduction to what's going on. I think someone is thinking about a question or not? Yeah. Do you want to think longer, or do you have the question?
No, I'll ask it.
Good.
Thank you. I was just thinking if you can connect the noise to any of human discernible attributes in a picture. For example, in the case of the cat, can you just have a small group of pixels that you have to choose, and you get a different color or something in this direction? Is there anything?
So it's interesting that you asked. So I wasn't going to talk about all of the different things you can do with diffusion models, but for example, one thing that you can do is you can, for example, take the Dali image here on the right, which is also of Salvador Dali, and then you mask out like one eye, for example, and you just mask it out, and then you add random noise, and then you just run the diffusion process on that bit, for example, and then you could in the text prompt say green eye, blue eye, red eye, and then it would do that. And that's how a lot of these SD edit tools, for example, or these editing tools that I think Stable Diffusion also has like different editing, or people have used Stable Diffusion for image editing. You might mask out a bit and then say, I didn't like that astronaut, I want a different astronaut, he should look like a taikonaut, or he should look like a cosmonaut. Or I don't like that the ground isn't grass, and then I'm going to mark the ground and I say I want to run diffusion that's kind of nudge towards producing grass down here. And it usually, the way that you do it is you take the clean image, you remove a bit and add noise here, and maybe you also noise the entire image, which means you basically put it somewhere in the middle of this whole chain of like clean image and noisy image. You're here, and then you just run the denoising again, and it gives you a different result with different random seeds. That's how that works. Yes?
So a related question: if you can use the latent dimensions to say anything, like for the VAE you could have faces turning, that could be the latent dimensions, or like the height of the persons on whatever. Is there something similar here for diffusion models?
That's the next slide.
Great.
You're anticipating the question, very good. So how does this compare to a VAE? It's phrased in this. So Rich Sutton is a scientist mostly working on reinforcement learning, and he coined this phrase of the bitter lesson in this blog post from 2019. And kind of the main statement is written here, and it's the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. And he compares that to methods that do feature engineering by hand, for example. So more data and more compute. Like a general method that can digest even more data and even more compute will be better than if I handcraft something and I think very carefully about it, if I only use enough data and enough compute. It's a bit of an oversimplification in the way that I phrase it. It's a bit more nuanced, but that's kind of the general picture. And in this the diffusion models use kind of a very use a fixed inference, which is easy to optimize because we only ever jump to a single point, and every layer has a clear role, as I explained in the beginning. And the number of parameters in this model doesn't scale with the number of layers or the number of steps, because in a hierarchical VAE, each of those stochastic layers has its own parameters because it's an own Q distribution. You train this, you have this. In the very deep VAE, we saw there were lots of ResNet blocks for each of them. So if you wanted to double the number of layers, then you would have many, many more parameters. Whereas for diffusion models, we only have this one unit, and then we use the same unit at each step. We just tell it at which time step we are, so it's kind of conditioned on that. But otherwise, it's the same unit, so it's the same number of parameters. And if you want to do 2 and many steps, you need twice as much compute, but you don't have more parameters. So there's some very, very clever parameter sharing going on here. That means it doesn't explode. So it uses kind of the network capacity that you provide very differently, because it uses all the capacity for each step instead of sharing that between the parameters, and then the parameters argue with each other who should explain what. And during training, we can also subsample T, which is the layer number. So we only train basically one noise scale at a time. So layer here means time step. And in a VAE, as you remember, we need to actually go through all of the hierarchical layers, and then we need to go back all the way, which can be very inefficient because maybe we need much more training steps for the details and much less for the course information. But we always need to go through everything. Whereas here we can subsample and say we spend more time on the fine details and less time on kind of the coarse details, which kind of allows faster training, and we don't need to encode and decode fully at each step, but we don't just do a single one of those. And ultimately, so we talked about like how it's inaccurate that if you take noise and you only run the unit once, you're going to get a pretty bad image. And if you do it 1,000 times, you get a pretty good image, which means you can scale by compute how good the result should be. And there's like some, I don't want to say rigorous, but like at least well-motivated bounds. And I think probably those bounds are also quite rigorous in that if you took infinitely many steps, then the Gaussian approximation becomes exact and then actually recover the true image. And so you can scale by compute how much you want, which for VAE we can't do because we have a fixed number of layers. And then if you say, oh, I want my model to be more accurate, you have to train a new model. Whereas here you can say, I'm just going to make the time step smaller and kind of run it longer. But I have that flexibility later on. And that's kind of how this is tied in. And then kind of addressing the question that you had, what did we give up when we moved to diffusion models? So typically, at least when we use the simple objective, we don't have a likelihood computation anymore. So we can't, I guess we didn't optimize the likelihood. And in principle, that means it could do mode collapse in the same way that a GAN might have mode collapse. Typically, empirically, we find that it doesn't to a certain degree, but it can happen, and you're not protected from that in the same way that you might be in a VE. We also gave up interpretable latent variables because in the picture that I showed you, we just had different noised versions of the image. So you could say, each of those noised images is basically its own latent space. And then the latent space has exactly the same dimensionality as the image, and we don't have interpretation. And that's what we gave up by fixing the inference. So because I said, you can think about the diffusion as we have fixed the inference, and we just copy and add noise. And that destroys information over time at a certain rate. But it doesn't make it interpretable in the same way that for a VAE, for example, it became interpretable because the latent actually had to learn credit assignment, and then credit assignment and bottleneck somehow together gave you this latent space that is structured in some way that you can then interpret, for example, as height or as turning your face. And that we don't have in a diffusion model. In a diffusion model, the way that you would do this is that you have this conditioning information, and then you could say, I want 45 angle here, 45 degree angle here, and then maybe interpolate in some way. And there are ways that people do this. Basically, you can say, I take these two images, I both noise them, and then I mix the noise of the two images, and then I decode this deterministically. And then it turns out, even if you kind of take this noise space and you average in this noise space, you get something that interpolates in the image space to some degree. So there are ways that you can do it, but you lose the interpretation of this being a latent space because it's just a noisy image now in a way. And the inference process, which is fixed, is, okay, sorry, I missed one, yeah. So that also means there isn't really any representations, because in VAEs you can say this latent space is also a representation, a low-dimensional representation that I can use for compression. What's the representation in a diffusion model? Is it the noised image at time step 633? Is it the noisy image, but that's just drawn from noise? Is it kind of the bottleneck of the UNet at a certain time step? How should I think about this? And I think that's something that the community is at the moment working on. If you would like to use it for a downstream task, can you get a representation of the image out? For example, to classify it later on. The inference process is also very brute force in the sense that it's independent of the data distribution, because I said I just add random noise, and I did this with images of cats. If I had an audio signal, I would use the same thing. If I had video, I would do it in the same way. If I had molecules, unclear how I would add the noise there. So it's the question is, how do we handle discrete data in this setting? Because this always assumes adding a little bit of noise, which is continuous. It might be that it works very well in images, and there was this motivation with the frequency spectrum that it kind of makes sense of like drowning out high frequency information first and coarse information later. Maybe that doesn't apply to other data sets, and then this type of noising doesn't make as much sense as an inference procedure. And ultimately, sampling can be very slow in that in a VAE or in a GAN, it's a single feed forward pass, whereas here we have to actually apply the UNet tens or hundreds of times. And all of these things are very active areas of research where people look into making better choices, improving the sampling, improving the objective, improving the model. So there's a lot of work and activity going on, and I don't think that in 2 years' time we'll use, already now I think many of the state-of-the-art diffusion models don't use exactly what I presented to you. This is basically the first iteration from 2020. Already now we use slightly different models that are still very much like this, but have lots of tweaks and changes everywhere. And I think over time we'll probably move to something that works slightly differently, but it's still inspired by all of this. And I didn't present the ODE and SDE formulation, so that you can think about this as continuous time. You can write down stochastic differential equations that do a lot of things for you, and then you can try to connect them back to what I talked about. But it looks like all of these stochastic differential equations seem to become less and less important, and a simple approach that you can scale very well seems to work much better. And then some of the theory ties into the last point about like, how can you set it up in such a way that you don't need that many sampling steps? But yeah, as I said, all of these things are kind of very active areas of research, and if you want to get into those, then I think it's an interesting time, but it also moves very quickly. So if you have an kind of archive alert, then you get an email every day about 10 new papers that come out in this area. Cool, so that's my presentation. Thank you very much. And now I'm happy to take any more remaining questions.
Hey, I'm curious about your thoughts on pros and cons of diffusion models and normalizing flow, in particular Bayesian inference. Interesting.
So I guess normalizing flows have the advantage that you can evaluate the likelihood, and I guess especially when you are in a Bayesian framework and you want to use it as a component part, then that fits perfectly in, because it's a likelihood distribution, or it's a distribution, and you can tie it in with other distributions that you have. You can use it as a prior, as a posterior. We'll learn about this from Steve, I think, later today and tomorrow. So that naturally fits in, whereas in the way that I presented diffusion models here, especially with the simplified loss function, you don't really get likelihoods out. There are ways to compute likelihoods, but because of this iterative sampling, it's a bit like in an autoregressive model where evaluating the likelihood can be very expensive. So as I said, you can go through this long derivation, and then you get an objective that optimizes the likelihood instead of just this L2, because there are these weighting factors. And then you get something that approximates likelihoods much better. And I think that people are looking into this, but I think especially because of all of the UNets and the iterative application of that, if you want to optimize something, you have to take gradients through all of these steps, and that becomes extremely costly, which I think is why people are starting to look into whether you can speed that up, or come up with like different ways of optimizing. In principle, you should be able to use diffusion if you use it in this kind of more Bayesian setting. And for example, there was this paper by Dirk Kingma and others from Google that looked much more in the likelihood-based formulation, and also for training and also for the interpretation. And that seems to work decently well. So I think there are ways you can tie it in, but it doesn't work as seamlessly, I think, for now at least, as flows. But in terms of the modeling capacity, I think this, because there's no constraints on the UNet and on the networks that you can use, other than like flows always you need to be invertible on a single layer, whereas this is not the case here. So this might ultimately be more powerful, but I think it will be more difficult to integrate. And I think people are starting to use this, like stable diffusion, I guess you can think about, you have this autoencoder model and then you fit a prior to the latent space, and the prior is just this diffusion model. Because you draw from noise, you go to a latent in this VQ gun space, and then you decode that using your pre-trained decoder. So it's an autoencoder model where you fit a prior. You can think about it like that, I guess. And so in that sense, it is doing Bayesian or model selection in this Bayesian model.
And if I can, I ask another one.
Mm-hmm.
I think the forward diffusion process that you showed is very, very related to what in the MCMC world they call the precondition Crank-Nicholson proposal. So where the purpose is that you converge to an asymptotic distribution that is independent of the initialization, so that x0. And there are ways to accelerate this, at least in the theory. You can precondition those beta factor that you with a matrix and just keep in the relation. And I was wondering if this has already been looked at in the diffusion literature.
So I think the honest answer is I don't know. I know that a lot of literature, like speeding up the sampling is something that people start, if you think about, like one way is to go into this latent space, so you sample in a lower dimensional space, which what stable diffusion is doing. It's also more memory efficient than modeling directly in image space. You have these cascading models, but it's also about just speeding up the sampling. And people have tried lots of different things motivated from the whole SDE-OD literature, using kind of specialized optimizers that use the structure of the problem. I don't know if they looked into these connections. In parts, the way that, I presented kind of one view of diffusion models from this kind of Jonathan Ho type approach, but there were a lot of precursor works that think about it differently in terms of bridging distribution. So instead of having a continuous time, or in this case discrete, but in very many small steps, you could just think about like having a little bit of noise, having intermediate noise, and having a lot of noise, and then looking at it in terms of like these bridging things. And that kind of ties in, I guess, a lot with annealed importance sampling or these type of annealing ideas in general. And I think that's very interesting, and I'm not sure whether people have done that in this specific context yet, but if not, then you should get onto it now.
Thanks.
More questions? Okay. If not, then let us thank Matthias. I think this was your final talk in this session. And if there are more questions, I'm sure he will be very willing to talk to you. So thanks, Matthias. This was a great series.